Hello, everyone. In this video, we will introduce shortest path. For example, we have the US map, and we want to travel from Seattle to Miami. What is the shortest path? This problem can be solved using the graph algorithm to find a shortest path between two vertices in the graph. This is the algorithm we're going to use to find shortest path. In the process, this algorithm finds the shortest path from a single source to all the vertices in the graph. The input for this algorithm is the graph with the vertices and the weighted edges. Assume all the weights are non-negative, and the output is a shortest path tree. We're going to start from a source vertex. Let T be a set that contains the vertices whose paths to the source S are discovered. So all these vertices, we know their path to the source is in T. Initially, T is empty. Set cost of this S is 0, and the cost of V is infinity for all other vertices in V. While size of D is less than n, we're going to find the U not in T with the smallest cost. Add U to T. For each V not in T and UV is in E. So we're going to see the cost of V if it's greater than cost of U plus WUV. We're going to update the cost for V and also update the parent for V. This algorithm is very similar to the algorithm in the preceding video for finding minimum spanning tree. We use cost, but here cost means different things. In the preceding algorithm, the cost just means that you have this vertex not in T, and whose shortest distance to one of the vertices in T. So that's just the one edge. Actually, it's the cost of V is an edge. It's a vertex not in T to a vertex already in T. So what is that minimum cost? Here in this shortest path algorithm, the cost of V is the distance from V, so V is not in T, to the source. That is the cost. So if we don't know it, that's infinity. If we know it and we have a cost, in the process, we keep updating it. So we will find a better way and to get the shortest distance. All right, so let's look at this diagram here. So this is the T. So here's the source. So we need to bring a vertex from this V minus T to T. So which one we're going to bring? We bring the one, and that has the shortest distance to S. All right, so let's see, we're going to bring U here. And after you bring U here, you can look at all the neighbors of U that is not in T and see if we need to adjust their cost. Here's the example. I'm going to start from this vertex 1 is my source. So the cost for 1 is 0 and all the others are infinity. So the parent of 1 is -1, indicating it's a root in the shortest path tree. Which one we're going to bring to T? So this is going to be this 1. So 1 is in T. And after this, we're going to update the neighbors, the cost. So 2 is now becoming 5, 0 is 8, 6 is 9, and 3 is 10. All right, so all of this, which one is smallest is 2. And here, this vertex 2, and so we're going to bring 2. After you bring 2 into T, so you're going to adjust the cost. The cost for 0 was 8, now it's going to be 1 plus 5, it's going to be 6. So that is the shortest distance to 1, from 0 to 1. So now you see the next, this is right here, is 6. All right, so after you bring T and you go into the 2 into the T, so you make this adjustment. And so now you're gonna pick the smallest one and not in T, so that is going to be this 0. So this is 6, so this is. All right, so this is the process. Eventually, you bring all the vertices into T, and you get the shortest path tree along the process. Let's look at the implementation of this algorithm. So this is my algorithm. And here is the source code. So this is the shortest path tree, has the cost and has this shortest path tree, the constructor, and the get cost and print all path. All right, so let's look at this program. So this is going to be right here. So let's look at the shortest path, get shortest path. Starting from source vertex, all the cost, infinity, except now the starting vertex. And the parent array is created, and the source vertex, the parent, is -1, indicating it's a root. The T, and we use the list because we want to keep the order of all the vertices inserted into T. And now writing this, the loop yt dot size is less than get size. So we're going to discover the lowest cost for the vertex not in T. And now if we don't find it, it's -1, so that means the graph is not connected, break. Else we're going to add this vertex into T. And now we're going to adjust the cost for all the neighbors of U. So look, when you adjust the cost, and so here is the vertex is not in T, and now also here is the cost of this vertex is greater than the cost of this U. This is the one plus the weight of UV. So U and with this vertex. After all this done, and we create a shortest path tree, and we have the source vertex, the parent, and T, and also the cost. And this is the shortest path tree, so we keep the cost here. See, this is good about this if because you want to get the cost for any vertex to the root, the distance. So this cost array, and we'll give you that information. All right, here is a test program. So we're going to write a test program to test the shortest path. This is my vertices, and this is the edges for the US map. Creating a weighted graph using vertices and edge. And now let's get the shortest path is from Chicago. So the index, graph1.getIndex. And now you can print all this path to Chicago. And let's find the shortest path from Houston to Chicago. So graph1.getIndex Houston. So in the tree.getPath. So this tree has this, it's a search tree. You can get the path. So that's the path. And you can also get the distance of this path, and by invoking the get cost. So I'm going to go here, look the program here I have. So let's do this now. The shortest distance. So this is to get the path, and so this is the path. So I'm going to also print the shortest distance from Houston to Chicago is. So what is this? Is graph is tree 1. So that is tree. It's a shortest path tree. Dot get cost. So this is the method here, get cost. And so we need to have the index for the vertex Houston. All right, let's give it a try. So this is what I have now. It's the shortest path. Okay. And the distance is this right here. The shortest distance from Houston to Chicago is this. So if you want to find the shortest distance from Dallas to Miami, so what you do? Well, you have to create a new tree. So here you're going to say, I'm going to have this tree is rooted at Dallas, and Dallas to Miami. So I'm going to now the shortest distance from Dallas to Miami is, so here is Miami. All right, so let's give it a try. And that is the shortest distance. Thank you for watching this video. See you on the next video.